In this video, I go over the derivative of the trigonometric functions. And because that goes by so quickly, I'm also going to go and remind you a few rate of change problems and look at the slope of graph and equation of tangent line problems. So let's just dive right in and find the derivative of the sine of x. So to do so, the derivative of the sine of x in terms of x is just the limit as h approaches 0 of the difference quotient. So, in order to find out what that limit is equal to, I want to rewrite that difference quotient. I want to rewrite it in such a way that certain expressions appear whose limits I know how to find easily. Now, you've seen me do this before. In particular, I like to make those limits appear because I know the first one is 1 and the second limit is 0. So to do so, notice that the sine of x plus h, that is the sine of the sum of two angles. There is an addition formula for sine. I'll just use it. So that gives you then that the limit as h approaches 0 of the sine of x times the cosine of h plus the sine of h times the cosine of x minus the sine of x over h. Well, I'm going to take that now and separate it into two fractions where each fraction would actually be a product. In each product, one of those two limits will appear. It winds up being this right here. Feel free to go back, add those back up to get the original fraction to see that these are actually equivalent expressions. Now the limit of a product is a product of limits. A limit of a sum is a sum of limits. So I can push the limit through all these pieces provided they all exist. And the limit of the sine of x as h approaches 0, that's just the sine of x because x is not changing. It's a constant as h goes to 0. The limit of the cosine of h minus 1 over h as h goes to 0, we know that's 0. The limit of the cosine of x as h approaches 0, that's just the cosine of x. Because x is a constant, h is what's changing. Finally, the limit of the sine of h over h as h approaches 0, that is 1. So just simplifying that particular sum of products, we get the cosine of x. That leads us then to this result, that the derivative of the sine of x is cosine of x. That's kind of neat, isn't it? So if everything was great in the world, if everything was good and pure, the derivative of cosine would then be sine, because we have this nice symmetry, and we as mathematicians like symmetry. Alas, though, it's not true. So let's just do a couple examples of taking derivatives of expressions that contain a sine of x in it. For example, this first one, the derivative of e to the x times sine of x. Notice the very last operation you see in between all the objects is a product. So I need the product rule first. That would be the first factor, the derivative of the second factor in that product, plus that second factor, times the derivative of the first factor, where I'm using the derivative operator to keep track where I'm at. That then is e to the x, parenthesis, I know the derivative of sine, it's cosine, plus the sine of x. And the derivative of e to the x, I know what that is, that's just e to the x. Next, notice that there's a common factor of e to the x. If there ever is a common factor between the sum of products or difference of products, you always want to take it out because it makes the later steps of setting this equal to 0, the primary use of derivatives for quite some time, makes that easier. That's the way I would write down the derivative. Don't worry though, they're actually both correct. If someone said, what's the derivative? They're both correct. It's just we don't write the middle one, we write the last one. Next, I want to know the derivative of the sine of x over x. Now the very last operation here between all the symbols is division. So I'll need the quotient rule. The quotient rule requires a long division bar, which you don't often know how long it should be, so you erase it or extend it as we need. Then you have the denominator, the derivative of the numerator minus the numerator times the derivative of the denominator, and that's all over the denominator squared. And notice I'm putting that right under where the subtraction is. So think of it like a balanced seesaw. Some people also will say low d high minus high d low in order to remember the way the quotient rule works. Now that then is equal to, big long division bar, you have an x, and the derivative of sine of x is just the cosine of x. You have minus the sine of x, and the derivative of x is just 1. That's all over x squared. Lastly, we'll just simplify that. We put the monomial first, then the trig function. Don't write sine of x times 1. That's silly. Just write sine of x. And that's all over x squared. That's it. That would then be the derivative of the sine of x over x with respect to x. So let's now go and find the derivative of the cosine. Well, it's almost exactly the same derivation as I used in order to find the derivative of the sine, but I'll go through it again just so you see it. The derivative of the cosine of x with respect to x is the limit as h approaches 0 of the corresponding difference quotient. But we then have the cosine of x plus h. That's the cosine of a sum of two angles, and we have an identity for that. So I'll just replace that portion with what I know it's equivalent to. That gives me this. Once again, that fraction can be written as a sum of products. Each product, one is a fraction, one does not. I'll just do that part for you now. Feel free to go look at what you see, add it back up to get one fraction to convince yourself that they're equivalent expressions. Now, a limit of a sum is a sum of limits. The limit of a product is a product of limits provided all the limits exist. And we can find the limit of each of these pieces. In the end, you get the cosine of x times 0 minus the sine of x times 1. So that is negative the sine of x, or the opposite of the sine of x. That unfortunately gives us this rule, that the derivative of the cosine of x with respect to x is the opposite of the sine of x. It's not the sine of x. Let's try a quick numerical example. I want to know the slope of the graph of this particular function when theta is pi over 3. Now don't be thrown off by theta. We're just going to take the derivative in terms of that variable to find the slope or the rate of change. So what I need then is I need to know what's the derivative of this function with respect to theta. So I need the derivative in terms of theta applied to the sine of theta all over the cosine of theta plus 1. That requires the quotient rule. So that would then be equal to big, long bar. I'd have the denominator multiplied to the derivative of the numerator minus the numerator multiplied to the derivative with respect to theta of the denominator. And then I have the denominator squared. That's the derivative. I just go back now and just kind of clean that up. So that's going to equal big long bar. I'd have the cosine of theta plus 1. The derivative of sine of theta with respect to theta is just the cosine of theta minus the sine of theta. And then the derivative of the cosine of theta plus 1 with respect to theta, the derivative of cosine of theta with respect to theta is negative sine of theta. And then I have the derivative of 1, which is just 0. And that's all over the cosine of theta plus 1 squared. So that would then be, in the numerator, I'd have a cosine squared of theta plus a sine squared of theta plus a cosine of theta, and that's entirely over the cosine of theta plus 1, that quantity squared. And that then would be, I'd get a cosine of theta plus 1 over a cosine of theta plus 1, that quantity squared. So after all this work, you get 1 over the cosine of theta plus 1. That's the derivative. I can now answer the question. I want to know the slope. So the slope of the graph at that point would then equal the derivative evaluated at the input, which in this case is just pi over 3. And that's 1 over the cosine of pi over 3 plus 1. That happens to be the cosine of pi over 3, you all remember, is a half. So that's 1 over a half plus 1. That is, in the end, just 2/3. That's the slope of the graph at that point. So let's go over a rate of change problem really quickly. If you have a weight that's suspended on a spring, and then you pull that weight downwards, say 5 meters below its equilibrium point, and then you release it, the object will then oscillate up and down. Let's suppose that the position of the weight in time is given by this formula, where x equals 5 times the cosine of t, and x is the position in time. Also, we're going to mark downwards as positive. So if I have a positive displacement, it's actually below equilibrium. 0 is considered, that position is considered equilibrium. I want to know then, what's the velocity of the object at any time? Well, that's easy, because the derivative of position with respect to time, that's velocity. So the velocity would then have to equal, it'd be the derivative in terms of time of 5 times the cosine of t. But that would then be, we know the derivative of cosine is sine with a negative, so that's minus 5 times the sine of t. That gives you the velocity at any single moment in time. Now you may wonder then, how fast can the object go? Remember that speed is the absolute value of velocity. So speed of this object would be given by the absolute value of that velocity, which is 5 times the absolute value of the sine of t. So then I want to know what's the fastest it could be ever. Well, that would require us then to find the maximum value of the sine function. But we know that from trig. The maximum value of the sine of anything is 1. So the biggest that could ever be is 5. Now the next question would be is when does it happen? Well, that would have to happen whenever the sine of t is, in this case, 1 or negative 1. So it happens many times. But the soonest time would be when t is pi over 2. When t is pi over 2, the sine of pi over 2 is 1, and so the speed is at its maximum, which is 5. Okay, let's go ahead and try to find the derivative of the secant of x. Now the nice thing is we don't now have to go back to limits. Instead, we'll use the derivative rules we already have. To find the derivative d dx of the secant of x, that's actually the same as writing the derivative of 1 over cosine of x. That way I can use the quotient rule. That would then be big long division bar. I'd have the denominator, the derivative of the numerator minus the numerator times the derivative of the denominator. And that's all over the denominator squared. So that's the same as writing the cosine of x times 0 minus the derivative of cosine is negative sine of x. And that's all over the cosine squared of x. So that would be then, that's just the sine of x over the cosine squared of x. That's the answer. That's the derivative. But we don't like that answer. The reason we don't like the way it's written is because, well, we have the derivative of secant. It's just one little trig function. It'd be nice to get the answer as, so there's no quotient anymore. After all, there wasn't a quotient in the beginning. Well, but the secant function is directly related to the tangent function. It's kind of like it's a family. So very often when we write trig expressions, we try to stay within these Pythagorean families. If we have sines and cosines, we tend not to have anything else. If we have secants and tangents, we tend not to have anything else. If we have cotangents and cosecants, we tend to have nothing else in the expression besides them. So here, notice you can write this as, it's really 1 over the cosine of x multiplied by the sine of x over the cosine of x. So we get then that the derivative of the secant of x is really the secant of x, being 1 over cosine, times the tangent of x. That's the derivative of the secant, which is really unfortunate, because then the derivative of something that's simple becomes something that's more complicated. There's more trig functions, and now it's a product. That's not good, but it is what it is. So without going through the rest of them, here are the derivatives of the remaining trigonometric functions. I've also paired them up in a way that I hope you can remember them. The derivative of tangent is secant squared of the angle. The derivative of the secant of the angle in terms of the changing angle is just the secant of the angle tangent the angle. Now notice the derivative of the cotangent of the angle is negative the cosecant squared of the angle. See, the derivative of tangent is secant squared. The derivative of cotangent is negative cosecant squared. They're connected. The derivative of cosecant is negative cosecant of x times the cotangent of x. Again, notice the derivative of secant is secant tangent. The derivative of cosecant is negative cosecant cotangent. They're connected. So if u is equal to the secant of x, I want to know what u double prime is. So if you remember double prime, that means second derivative. So we already know what u prime is. It's just the derivative of secant, which we now know is secant of x tangent of x. So if I want the second derivative, I need the derivative of the derivative. So I take the derivative of the secant of x tangent of x. That will require a product rule. So it's the first factor, secant of x, times the derivative of the second factor, that's the tangent of x. Then I have plus the second factor, that's the tangent of x, multiplied by the derivative of the first factor, that's the secant of x. That then would be the secant of x, and the derivative of tangent is secant squared of x. Then I have plus the tangent of x, and the derivative of secant of x is secant of x tangent of x, which gives me the answer, which will be in the end secant cubed of x plus the secant of x, the tangent of x, where the secant is, well, the tangent is squared. Now, if you want to, you could pull out the common factor of secant here, but it's one of those maybe we don't care too much. But you could if you wish to. It doesn't really seem to simplify any further, though. So I would probably just leave it alone. As an application, let's go ahead and try to find all the points in the graph y equals 2x minus 4 cosine of x, where x is going to be limited between 0 and pi over 2, that has a horizontal tangent line. Now, if you recall, I did a problem like this before. If we have a horizontal tangent line, then the slope of that tangent line must be 0. But the slope of the tangent line is the same as the slope of the graph. But the slope of the graph is the derivative evaluated at that point. So you're really just saying this problem to solve that the derivative is 0, slope of the graph is 0 to get a horizontal tangent line for x. So I just need the derivative. So the derivative would then be the derivative of 2x in terms of x is 2. You then have minus 4. And the derivative of cosine is negative sine. That multiplication makes it be a plus sine of x. So if we had 2 plus 4 sine of x equal to 0, that would imply that the sine of x is negative a half. And there's only two angles where that's true in the angle range I gave you. That angle range being 0 to 2 pi, one such solution would then be 7 pi over 6. And the other such solution in that angle range is 11 pi over 6. Now those are just the x-coordinates. I wanted the points. So for the x-coordinate of 7 pi over 6, the corresponding y-coordinate is 2 times that angle minus 4 times the cosine of 7 pi over 6. So then that is 7 pi over 3 minus 4 times the cosine of 7 pi over 6. 7 pi over 6 is in the third quadrant, so the answer is negative. The reference angle of 7 pi over 6 is pi over 6, and the cosine of pi over 6 is the square root of 3 over 2. So the y-coordinate is 7 pi over 3 plus 2 times the square root of 3. So that point then is 7 pi over 6, comma, 7 pi over 3 plus 2 square root of 3. That is one of the 2 points. Because there's another x-coordinate, the other x-coordinate is 11 pi over 6. In that case, the corresponding y-coordinate would wind up being 2 times that. That's 11 pi over 3. You then have minus the cosine. So it's minus the 4 times the cosine of that angle. But the cosine of 11 pi over 6 is actually positive square root of 3 over 2. So you would get positive square root of 3 over 2 times 4, and that would then give you 2 square roots of 3 being subtracted. So the point then in this case is 11 pi over 3 Oh, sorry, 7. It's 11 pi over 6, 11 pi over 6, comma, 11 pi over 3 minus 2 times the square root of 3. That's it. That's the other point. Let's find all the points on the curve y equals the tangent of x, whose graph looks like this between pi over 2 and negative pi over 2. I want to find all those points on this guy's graph so that has tangent line. Let's just say this is the point I'm interested in, and here's the tangent line I'm considering right now. Oh, I missed the point. Oh, you get the idea. That is parallel to the line y equals 2x. Now the graph of y equals 2x would look kind of like that. So I need a way to connect these two. Well, if they're going to be parallel lines, their slopes are equal. So the slope of the line, though, is easy. It's just 2. The slope of the tangent line is just the derivative evaluated at that point. So let's just go ahead and find the derivative. So the derivative of y in terms of x is just the secant squared of x. So I'll solve that the secant squared of x equals 2 for all x. And I'm only going to look from negative pi over 2 to pi over 2. The reason is that the tangent graph is periodic. It just repeats over and over and over. The tangent is periodic. So if I have a point on the graph of the tangent in this range, so the two lines will be parallel, when I translate the graph over by pi to get another copy of the tangent graph, I'll get another point on its graph where its tangent line is also parallel to y equals 2x. So I'm not interested in looking at the infinite number of such points. Let's just find the ones in this range only. So that would then mean then that the cosine squared of x has got to be a half. That means the cosine of x must be plus or minus the square root of 2 over 2. But in this angle range, there's only 2 angles where the cosine is that number. That would be x is negative pi over 4 and pi over 4. So I can find the points pretty easily. The points are the x coordinate would be pi over 4. The y coordinate is its tangent, which is 1. And the other one is negative pi over 4 is the x coordinate. And here the tangent would be negative 1. That's it. Those will be all the points on this graph in this range from negative pi over 2 to pi over 2, so that the tangent line is parallel to the line y equals 2x. So as our last little application, don't forget that you can use limits. You can, as our last little application, let's go find these limits. Now, notice that the derivative of all these trig functions exist in the domain of their function. So those functions are all continuous. To find a limit then of a trig function is just a matter of taking the limit of what's inside of it. So if you really wanted to, you could take the limit of the secant of all of this by first saying take the secant of the limit of what was inside instead. That's provided that the limit exists. But the limit laws push through pretty much everything. So the limit of a sum is a sum of limits. The limit of a constant multiple is a couple of limits. The limit of a composition, that's the tangent of pi over 4 secant of x. That's a composition. Is just as long as the outside function is continuous and tangent is, you just take the limit of the inside. So you just push the limit through everything, provided that it all exists. So this answer is pretty easy, because in the end this function is just continuous at 0 anyway, because it's a sum difference, constant multiple, composition of functions we know that are continuous. So the result's continuous. So the result is the secant of e to the 0 plus pi times the tangent of pi over 4 times the secant of 0 minus 1. Just going back and evaluating that, that's the secant of 1 plus pi. That would be the tangent of pi over 4, because secant of 0 is 1, and then minus 1. And that would give you the secant of 1 minus 1, that cancels. The tangent of pi over 4, well, that's just 1. So you have 1 times pi. This is the secant of pi. And the secant of pi is negative 1. That's the answer. That's how to find that limit. That's because the functions are continuous. So you can just push the limit through all of it. On the other hand, this one is a little more tricky. But you should notice that if you were to say, suppose f of theta is temporarily just the tangent, defined to be the tangent of theta, then this is really the limit as theta approaches pi over 4 of f of theta minus f of pi over 4, because the tangent of pi over 4 is 1, and it's all over theta minus pi over 4. So you recognize that is just the derivative. So that is the derivative of this function, but evaluated at pi over 4. So let's just find the derivative of this function. So we know the derivative of tangent is secant squared of theta. So this is then the secant squared of pi over 4. But the secant of pi over 4 is just the square root of 2, and I'm squaring it. That gives me 2. And that's how to find that limit. So notice you don't have to use the limit laws to get the answer, because a lot of those limits that you did that were actually kind of tricky, that in the end had 0 over 0 when you just plugged in the number, they were actually derivatives usually. And all you have to do is just recognize it this way to get the answer quickly. And that gives you a basic introduction to derivatives of trigonometric functions. And I also went over a couple examples and applications just to remind you of that connection between the derivative and the slope of the graph, slope of the tangent line, and also rate of change.